Okay, welcome back everybody. On to lecture 9. I'll also mention that the second assignment got posted over the weekend, so please take a look at that. You have about a week to do it. And the first assignment is being graded, so hopefully we can get the marks back within a week or two. And you'll get I'll post the solutions actually today or tomorrow, so you can have a look at the solutions even before the actual grades come out. I also wanted to say thanks for the nice suggestions. So many people put forth very interesting suggestions in terms of the topics and stuff, the mailbag topics on the last question of the first assignment. Some of the suggestions were things that are already in the course, so that makes me feel good because you want to know what's in the course. That's great. And then there's also other interesting suggestions that we might have time for at the end. Okay, so last time most of the class was spent applying the Coriolis force quantitatively. So we just did a little reminder of the Coriolis force concept, and so this idea is you can sort of think of it as a really good sort of conceptual model. If you're standing on a merry-go-round and you try to throw a ball, even though if you viewed it from not on the merry-go-round or you viewed it from space or something like that, that's just the wind?
Yeah. It's crazy.
Haunted. So the ball would appear to go straight, but because the people on the merry-go-round are moving, things appear to curve, even though they're actually sort of going straight, and that's the Coriolis force. And then we had this formula. So this tells us how to compute the strength of the Coriolis force. There's two, so like everything in physics, it's a vector. So there's an east-west component of the force and a north-south component of the force. And the formula is related to the mass of the object under consideration. So that could be the mass of the parcel of air, or on the second assignment, it'll be the mass of a rocket. Omega is the rotation rate of the Earth. U and V are the east-west and north-south components of the velocities. And theta here is the latitude angle. So maybe in mid-latitude it's 45 degrees, for example, and sine of theta comes in. And what we and we also talked about how the Coriolis force sort of results from the fact that the Earth is rotating, and also that it's rotating at different rates at different latitude bands. So it's fastest at the equator and slowest up towards the pole. And that leads to this phenomenon that the Coriolis force, the strength of that force, so basically how much things appear to curve when they're actually going straight, it depends on where you are. So it's the weakest at the equator. In fact, it's 0 at the equator. And it's strongest towards the poles. And the fact that it's weak at the equator, you can really see in this diagram, which shows where hurricanes form. And there's this very conspicuous gap right along the equator where there are no hurricanes. And that's because the Earth sort of behaves almost like it's not rotating at the equator. That's a little bit of a weird statement, but there's a mathematical sense in which that's true. So the Coriolis effect is very weak at the equator. And we applied these formulas and we calculated the Coriolis force on this big slab of air that we said we just sort of drew a box sort of south of Newfoundland there, and we worked out how strong are the pressure forces and how strong are the Coriolis forces. And we found this very interesting thing that with our very rough estimate, those two forces were quite similar in terms of their strength. So they weren't exactly the same strength, but they were very close, within a factor of 2. And this is this thing we call geostrophic balance. So geostrophic balance is this observed fact, and there's also sort of a theoretical basis for it, that in atmospheric flows and in the ocean, the Coriolis force and the pressure forces are very closely balanced. And so they sort of point in opposite directions and they sort of push on each other. And so this block of air has a Coriolis force pointing in this direction and a pressure force pointing in that direction, and they sort of cancel each other out. Okay, so today we're going to now look at what are some of the implications of the Coriolis effect on the atmospheric circulation. So we talked before about warm air rises and cold air sinks, and this sort of sets the air into thermal motion. But what exactly does that look like on the largest scales? What do the global wind patterns look like? And then we're going to move on from the global wind patterns to sort of smaller scale stuff like weather. So it's still large scale, like maybe the size of a province, for example, but smaller than the whole continent or the whole global scale. And this is going to tie us into the idea of weather prediction, which comes around to this very, very fundamental physical idea of chaos. And we'll talk about chaos a little bit. Okay, so when we first started talking about what sets the atmosphere in motion, we had this idea that it's driven thermally. So the sun heats the Earth more strongly at the equator, so you have warming here, and less strongly at the poles, so we have relative cooling here. And so you expect, if the planet wasn't rotating, you have the warm air rises, you have rising air at the surface in the equatorial region, and that creates this planetary scale convection cell with sinking over the poles. But I mentioned last time that if you try to set this up on a rotating Earth, there's a problem because of the Coriolis force. So as this air rises up into the upper levels of the atmosphere, so maybe this might be the top of the troposphere, so say 10 kilometers, and it tries to go north, as it moves north, it has a velocity. It has that v velocity, and in the Coriolis force formula, if there's a non-zero velocity, you get affected by this Coriolis force. And so this thing is this airstream is going to get deflected to the right, which means it's going to, instead of going north, it's going to go east and sort of wrap around the world around a latitude circle. And so this is actually why we end up having jet streams in the mid-latitudes, is partially because of the Coriolis force acting on this convection cell. So this model of the non-rotating Earth and the global scale cell is not accurate, although it's a useful conceptual model. And so now we're going to look at how does this work on the real in the real atmosphere. And so this is the cartoon diagram that I like to use. I think this is from the textbook. And it really encapsulates a lot of different features of the global atmospheric circulation. And there's kind of a lot to digest in this diagram, so I'm going to go through it piece by piece. But the first thing I'm going to focus on is these convection cells here. So the red part of it means you have warm air that's rising. The blue part of it means you have relatively cold air that's sinking. And what we can see in this cartoon, and I'll show some data now in a minute, is that instead of having one cell, we have rising at the equator and then sinking at the poles, that one large planetary scale cell gets broken up on the rotating Earth into 3 cells. And they all have names, so these are all, so in the history of meteorology, at some point these were discovered, right? Like there was a point in history we had no idea. You maybe know the wind is blowing west right now at this moment, but what's the global structure? Nobody knows. But so these cells are sort of named after some of their discoverers. So the Hadley cell, so Hadley was an old school meteorologist, is the tropical one. So the Hadley cell is the most important part of this 3-cell structure because it's the strongest. We'll see in the next slide with the real data, it's very strong. And the Hadley cell is exactly sort of what you would expect. So you have rising at the equator, we have warm air, and then it starts to move to the poles. But then instead of getting all the way to the poles, it gets to about 30 degrees north, and then it sinks down. So we have a cell that goes between 0 and 30 north. And then the mirror image of that is between 0 and 30 south. So all of these cells, they're symmetrical, or they're sort of a mirror symmetry about the equatorial plane. So that's the Hadley cell. And then if you move north, between 30 and 60 north, we have this counter-rotating cell that's called the Fitzgerald cell. So Fitzgerald, some other famous meteorologist. And in this case, we have sinking air at 30 and rising air at 60 north. And then if we move all the way up to the poles, we have what's called the polar cell, which is counter-rotating again with sinking or subsidence over the poles. So that's consistent. So cold air likes to sink. So this is the coldest part of the climate system. So we have sinking air here and then rising at 60 north. And the way that I like to remember these cells, or the way that I sort of, like a mnemonic or whatever, is I always just think of the Hadley cell, because we know that there should be rising air at the equator, and that's the same, that we have warm air there, we have a low surface pressure, we have this convergence coming out at the surface. So we have rising air here. That's also consistent with, we've talked before about the intertropical convergence zone, the ITCZ, and that there's all these clouds at the equator, lots of rain. That rain and those clouds are associated with rising air. So you can remember that there's rising air at the equator. And then if you just remember that there are 3 cells and that they fit together like interlocking gears. So when one is going down, the neighboring one is going down. You can just kind of fill them in like as if they were sort of gears that fit together. And so we have the Hadley cell, that's the strongest, then the Fitzgerald cell in the mid-latitudes, and then the polar cell up north. Okay. Now, this is a cartoon diagram. But if we look at the data, this is from a classic climatology textbook. We see a very similar structure emerge in the data. It's just not quite as pretty. So the top panel is what we normally view as the cell structure of the atmosphere. So the way this plot is oriented is that the South Pole is down here, the North Pole is over here, the equator is in the middle, and then we have the vertical axis is height. So this is from the surface up to the top of the troposphere. And if we look in the center here, we have in the middle of this diagram, we have rising air, so that the contours are showing this thing called stream function. But you can just think about it as the air sort of follows these curves. So we have rising air in the center, and we have a cell in the northern hemisphere and a cell in the southern hemisphere. This whole thing is called the Hadley cell. And then when we go into the mid-latitudes, we've got this ferrule cell, and the ferrule cell is counter-rotating. And then at the poles, you can sort of hardly see the polar cell. It's there, but it's quite weak. And so this tells you right away, well, the Hadley cell is the strongest. That's the one that's moving around most of the air. And then the ferrule cell is weaker, and then the polar cell is much weaker again. Something that's very interesting to me about this structure is that this picture that's shown in the top panel, and also sort of shown in the cartoon, is the annual average picture. So this is if you just looked on average over the whole year, which way is the wind going, it's this picture. But in climate, we all know that the climate varies very much seasonally. So the summer is quite different from the winter. That's true pretty much everywhere. Some places in the tropics, there's not a lot of big seasons, but generally, wind patterns and stuff, they vary seasonally. So very often, when you're looking at annual average climate statistics, those annual averages kind of can conceal a lot of details of how things are different in summer and winter. Because if you just take an annual average, you're sort of averaging your Januaries together with your Augusts, right? And so you're sort of mixing your signals. And so it's interesting to look at how does this cell structure, this global atmospheric cell pattern, how does this differ from winter and in summer? So the middle panel here is the winter time. So DJF stands for December, January, February. And if we look at the winter case, so this is northern hemisphere and southern hemisphere, we see that the rising motion, so up top in the annual average, the rising motion happens in the Hadley cell, basically happens right on the equator. But in the wintertime, that rising branch has actually moved into the southern hemisphere. And also the cell is very strong. It's actually much stronger. The fact that there's all these extra lines and the lines are close together, that means that the winds are intensified. So this is a very strong cell. And then this rising branch is happening to the south of the equator. And then in the summertime, the reverse happens. And the rising cell, so again, we have this strong cell. And the rising motion is happening around 10 north, or maybe between 0 and 10. So it's happening in the northern hemisphere. And so generally what happens is the ascending branch, or the rising branch of the Hadley cell, it tends to be in the summer hemisphere. So in June, July, August, so the northern hemisphere summer, the rising is happening north of the equator. And in December, January, February, which is austral summer, so the summer for the southern hemisphere people, then the rising motion is happening in the southern hemisphere. And that sort of makes sense because you're going to have rising wherever you have the maximum insolation. So if it's summertime in your hemisphere, most of the rising air is going to be in your hemisphere. And another very important thing that jumps out to me looking at these three pictures is that when we look at the annual average, you see the cells are much, much weaker than they are in the individual seasons. And that's because these two cells in the DJF and the JJA seasons, they're sort of shifted relative to each other because the cellular structure sort of moves around. And then when you average those two things together, when you average together winter with summer, there's like cancellation that happens. And so some of the winds, when you average together, if you have positive numbers in the average and negative numbers in the average, they cancel out and the overall average is less, right? So, so actually, the strength of this Hadley cell is actually quite a bit stronger than the picture that you get from the annual average because seasonally it both shifts around and it's actually much more intense. Okay, but the basic cartoon picture of this top Hadley cell in the center, ferrule in the mid-latitudes and polar in the North Pole and South Pole regions, that's the sort of conventional picture that everybody has in their mind, but it is good to know that actually seasonally it varies and it's quite a bit stronger. Okay, so that's the cellular structure. But in addition to these, what are called meridional, so meridional means north-south pointing, so these winds are flowing north and south. And in addition to these cells, there are also high and low pressure zones. So when you look at a weather map, and we're going to look at that later, you typically see these L's and H's, the lows and highs. But there are also, and so those are lows and highs that move around, that are weather systems. But there are also climatological highs and lows. So there are just parts of the Earth where the pressure tends to be lower and parts of the Earth where the pressure tends to be higher. And these are also indicated in the diagram. So where you have rising air, so at the center of the Hadley cell, you tend to have a low pressure. That's called the equatorial low. And then, so you have a low pressure wherever you have ascending air. So at the center of the Hadley cell, you have a low pressure. At the rising branch between the feral and polar cells, you also have a low pressure. So this is called the equatorial low, and this one here is called the subpolar low. And you can see the low is here written on the interior of the diagram. And when you have low pressure, that tends to be associated with rising air, surface convergence. So where you have lows, the air is flowing into that low, and we'll see that's also true of weather systems. As you have surface convergence, rising air, then you tend to have clouds and precipitation. So we have in the equator, that's called the ITCZ, and in the subpolar region called the subpolar low. And then there are also high pressures, and the high pressures are where you have descending air. So right at the boundary between the Hadley cell and the feral cell, we have this cool descending branch. Descending air is associated with high surface pressure and surface divergence, so we have the air spreading out at the surface. Descending air, so we know that rising air tends to be associated with clouds and rain, because when the air rises, it cools, and then that cold air can't hold as much water, and so we get precipitation and rain. Descending air, on the other hand, tends to be very associated with clear skies and very little precipitation and dry conditions. And so if you look at 30, that's where there's at 30 north and 30 south, the global wind patterns are associated with subsidence or descent or falling air. That's clear skies and very little rain. And so that's where most of the world's major deserts are all around these two latitudes, 30 north and 30 south. So if you look in California, some of the major deserts in California are around that latitude. In Iran, in China, in Africa, there are deserts at these latitudes. And so this is called the subtropical high. And then another place where we have a high pressure is over the poles. So we have cold air over the poles, tend to have clear skies, subsiding air, and that's called the polar high. So we have equatorial low, subpolar low, subtropical high, and polar high. Now, all the names and stuff are not critical. You don't need to remember all the terminology. But you should be able to construct this diagram logically, just starting from the Hadley cell. Because you know we have these interlocking gears. When we have rising air, we have low pressure. Sinking air, we have high pressure. And even though the diagram has a lot of different pieces to it, it all sort of fits together in this logical way. And so it's not that hard to remember. Okay, so we have our cells, and we have our surface pressures. This is another way to look at the surface pressure. So this is just now a plot of the surface pressure versus latitude. So South Pole on the left-hand side, North Pole on the right-hand side, equator in the middle. And this plot is showing surface pressure. So we have our equatorial low, our subtropical highs, our subpolar lows, and then the polar highs are kind of a little bit hard to see at the edges of the diagram. Okay, so now the last part of the diagram, so we spend a lot of time on this, but it's sort of very important because this sets the stage for the winds that drive the ocean, is not just the meridional winds, which are these north-south flowing winds, but we also care about the winds that are blowing east-west. And those are called zonal. In meteorology, we use the term zonal means east-west, meridional means north-south. These cells are also associated with east-west winds, and you can use, logically, the Coriolis force to figure out which way the winds are blowing. And the key thing to remember is that with the Coriolis force in the northern hemisphere, when you have air that's moving a certain direction, the Coriolis force kicks it to the right, and in the southern hemisphere, it's the opposite. If you have air moving in a certain direction, the Coriolis force will kick it to the left of its travel direction. So let's just work through that and just think about what the implications of that Coriolis force are for what are called the global wind belts, or the zonal wind bands. So let's just look as an example. So this is the northern hemisphere branch of the Hadley cell. And if we look at the surface flow, so we're looking at surface winds here, because the surface winds are going to be the ones that blow on the ocean. So if we look at the lower branch of the Hadley cell, there's this airflow that goes from about 30 north down towards the equator along the surface. And so this air is flowing south. So if you imagine you're a parcel of air and you're flowing south in the northern hemisphere, then to your right would be west. And so what you see is on these arrows here are showing that the air is flowing south, but then it's also getting kicked to the west by the Coriolis force. And this creates a band of winds that are called the trade winds. And they're called the northeast trade winds because they come from the northeast. And this brings us to a little bit of confusing terminology. So you may have heard before the terminology of westerly winds versus easterly winds. those terminologies are a little bit sort of backwards because westerly winds does not mean that the winds are blowing to the west, it means they're blowing from the west. And easterly means they're blowing from the east. So here, these winds are northeasterly because they're coming from the northeast and they're blowing towards the southwest. And then if we look at in the southern hemisphere, the exact opposite is true. So we have a Hadley cell, this is the southern branch of the Hadley cell, and we now have north flowing air. So now if you're in the southern hemisphere, you're flowing north. Now you're kicked to the left by the Coriolis force. So if you're traveling north, then to your left is also to the west. And so we have what are called the southeast trade winds. So they're blowing north towards the equator, and then also west as they're kicked by the Coriolis force. So all through the equatorial region, from about 30 south across the equator up to 30 north, we have winds that are sort of blowing in towards the equator and also to the west. And those are called the trade winds because of their historical importance for like shipping and that sort of stuff. Spices, whatever. Okay, so that's the trade winds. Now we live in the mid latitudes, so we're around here, but on the other side. And in the mid latitudes, you can use the same argument, and what you find is that the winds blow from the west to the east, and they're called the prevailing westerlies, or the mid latitude westerlies. So here we have the Fitzgerald cell, this is the mid latitude cell, and here you have flow from about 30 north along the surface up to about 60 north. And as that wind moves north, it gets kicked towards its right, which is towards the east, by the Coriolis force, and that produces this band of westerly winds. Those winds are pretty strong. We'll see on the next couple slides. There's strong westerly winds between 30 and 60 north. And if we go down in the mirror image in the southern hemisphere, we have the southern hemisphere Fitzgerald cell. That air is flowing south, gets kicked to its left, which is east, and so we have another band of prevailing westerlies in the southern hemisphere mid-latitude. So the whole Earth is sort of like mirrored like this. So there's a northern trade winds, southern trade winds, and then in the northern hemisphere there's prevailing westerlies in the mid-latitudes. In the southern hemisphere there's also prevailing westerlies. And then when you get up towards the polar regions, you can just use the logic one last time. So in the polar regions we have air that's flowing from the polar sort of cap down towards 60 north. That air is flowing south. When southward flowing air gets deflected to the right, that's to the west. And so we have the polar easterlies, and there's also polar easterlies down in the southern hemisphere. And so a few pieces of terminology. Westerly means from the west, easterlies from the east, northerly from the north, southerly from the south. So you want to sort of be careful with your terminology. And then the key idea, again, is if you just remember that air rises at the equator, and you remember that the Hadley cell is in the middle, then you can construct the three-cell structure, the Hadley, Fitzgerald, and polar cells. You can construct all the lows and highs at the interfaces between the interlocking gears. And then based on the Coriolis force, which is to the right in the northern hemisphere and to the south in the southern hemisphere, you can construct the global wind belts, the trade winds, the westerlies, and then the polar easterlies. And so almost for sure, at some point on some evaluation, you'll be asked some aspect of this diagram, not necessarily to draw the whole thing, but you might be given a diagram like this that's unlabeled and you have to sketch in the winds or something like that. That'd be a very common type of exam question. Oh, and I'll mention one other thing, which is that between the wind bands, so there are certain places where the wind changes direction. So for example, if we're looking at the equatorial region, so we have these trade winds that are blowing to the west, and the westerlies which are blowing towards the east. So at some point here, the wind changes from going this way to going that way. And so if it's going from easterly to westerly, at some point it has to cross zero in between, and the wind kind of has to be weak. And so at the boundaries between these are called the horse latitudes, where the winds are pretty weak, and also right at the equator, the winds also tend to be quite weak. And those are called the doldrums. So you have weak winds right at the equator, the trade winds are off the equator, and then we have weak winds at 30 north and 30 south as well. And sort of one sort of concise way to look at this is now a plot of the wind bands. So we have South Pole, North Pole, and now the curve here is showing the east-west winds. And so what we can see is in the equatorial region from minus 30 to 30, we have easterly winds, so these are negative, it's plotted as negative values. Those are the trade winds. Right at the equator, there's the doldrums where the winds are weak. In the mid-latitudes, so around 40 to 60, we have prevailing westerlies in the northern hemisphere and in the southern hemisphere. And then the winds get weaker up towards the poles, but you tend to have these polar easterlies that are negative again. So one feature that I always like to comment on when we look at this plot is that the pattern of winds is symmetrical largely between the northern hemisphere and the southern hemisphere. We have the trade winds in both, the westerlies in both. But there are also some differences. And something that to me is really noticeable is that these prevailing westerlies in the southern hemisphere are about twice as high or so as the prevailing westerlies in the northern hemisphere. So the winds, the mid-latitude westerlies in the southern hemisphere are much stronger. Does anyone have any idea why it might be the case that the winds in the southern hemisphere in the mid-latitudes are stronger than in the northern hemisphere?
More ocean surface.
More ocean, yeah, so why would that matter?
More hot air circulations and stuff like that.
Yeah, so there's actually lots of different ramifications, but so if you look on the globe, there's more land in the northern hemisphere than in the southern hemisphere. So especially at those mid latitudes. And so the fact that the surface is of a different type is what controls this difference. And there's lots of different factors that come with the fact that it's all ocean in this region. But one big one's actually drag, which is that when you have wind that's blowing over trees and buildings and mountains and that kind of thing, that sort of just puts an arresting force, just a frictional resistance force on the winds. And so in the northern hemisphere, all these winds are blowing over the continents, and so you have lots of drag. But in the southern hemisphere, this is all blowing over open ocean, which is relatively smooth, and so you have very strong winds, and those very strong winds produce really, really strong waves. And so the southern ocean waves are really, really incredible, and that's largely due to the fact that these winds are really strong. Okay, so that's the global picture. And that's quite important because when we get to fairly soon, we're going to be talking about the general circulation of the ocean in all the different ocean basins. So like what causes the Gulf Stream, what are some other currents in the Atlantic and the Pacific, et cetera. And understanding that picture of the global wind bands is really important because those are the main winds that drive those circulations. But at a day-to-day level, we experience weather just as importantly as we experience sort of the climatological conditions. So the next little bit is to talk a little bit about how weather fits into this picture, and weather is being kind of the deviations from that climatological picture. So to start off as a general question, so we all sort of probably have a different way of saying the answer. But when we say weather versus climate, what's the real difference between those two? There's lots of different ways of saying it. Does anyone have an idea? Yes.
Well, the weather is like what's happening right now, where you are in the moment, and then the climate is like a long-term average of what's been doing.
Right. That's right. So, and you were going to say time scale. Is that right? That's the physicist way of saying it. So when we think about weather, it's instantaneous or maybe short time. Like maybe it's the weather over a couple days. The weather's been bad past few days, right? And then climate is like, what does January tend to be like in Newfoundland? Right, so we break these climatological records all the time. So for example, just a few weeks ago I saw that we've had the most days this year that were above 20 or something. It's like we had the most days. So it's been kind of, in some sense, the hottest year ever was this year. In some sense, there's how you measure the hottest year, well, lots of ways to do it. But so that's a climate question. So I think even on the slide I put almost exactly what you said. So the weather is the local conditions. So it's at a particular time in a particular place, the winds are blowing from this direction. Is it raining? Is it not? And then climate is kind of like the long-term average of weather. And there's a little bit of a, you have a little bit of freedom of choice when you define these things. Is what do you mean by long-term average? Do you mean average over 100 years? Do you mean average over 1 year? Do you mean average over a season? And so climate can sort of operate on various time scales. We can think about ultra long-term climate like Snowball Earth, or we can think about the climate of a particular month, for example. But weather is always a few days normally. And so probably we've all wanted to plan a wedding or some sort of any event that's outside. And it would be awesome if you could know, like in 2 months, is it going to be raining on that particular Wednesday? That'd be fabulous. But we can't do that And it turns out it's difficult to predict weather beyond about a week. So a weather forecast of a few days away is usually decently accurate. But if you want to predict more than a few weeks in advance, it's nearly impossible to get accurate predictions, especially for something like precipitation. Precipitation tends to be one of the hardest things to predict because it has to do with clouds. Clouds are very complicated, and other reasons as well. But climate, because it's this long-term average, in some sense it's easier to understand and a little bit easier to predict. And so we're going to talk a little bit now about, well, physically, what's the reason for that distinction? Why is it that we can predict things about climate? Like we can predict, for example, we always know, what the average weather is going to be like in September or October. We always know, like, it's a little bit cold for October, meaning we have some sense of what it should be like in October. But we don't have any particular sense of what it should be like on October 15th, right? That's something we don't know generally. So why is the weather hard to predict? So to answer that question, it makes sense first to just take a step back and think, how do we actually do this prediction? So how do we do it in practice, and then so what's the challenge? This guy is Niels Bohr. Doesn't do weather stuff. He did atomic physics. But he has this really funny quote: "Prediction is very difficult, especially if it's about the future." So generally, if we want to predict anything, so whether it's weather or whether it's stock prices or election outcome or whatever, generally how you do it is 3 steps. So the first thing is you usually need to know what is the system doing now. So what's the weather today? What are the stock prices today? What's the polling like today? So we get input data that tells us what is the system doing right now. Then we take that data and we pass it into some sort of model. So some kind of computer model, code, spreadsheet, whatever. Some sort of, usually it's a computer program. And then that computer program takes the initial data and it makes a future projection based on the input that you give it. And so this raises a question that for many years this didn't occur to anybody, which is what happens if the model output, so the second step, you put the data in and then it gives you the projection. What would happen if the model is super, super sensitive to the very, very tiny details of what you put in? Because if you think about it, if we make any assessment of the current state, so we measure the current weather, current stock prices, whatever, current polling, there's always going to be some margin of error in that polling. Our weather instruments are only so accurate. Polling has variability. Stock prices have variance also. So it depends on exactly what specific moment you measure the stock prices. They might be fluctuating around. So if our predictions are super sensitive to the input, that might cause a problem. It might make it very difficult to predict. And so it turns out that weather works like that. So the word that we use in physics and also in math is that it's chaotic. So the atmosphere is chaotic, and we all have a general sense of the word chaotic meaning complicated, crazy, hard to understand. But there's journals called the Journal of Chaos. There's books on chaos. So chaos theory, it's an actual real thing in math. It's just not like Jurassic Park. But so the discoverer of chaos, the first person to ever see chaos and understand it at all, was this guy, Edward Lorenz. This paper was cited 30,000 times, that's a lot, in 1963. And he wrote this sort of nondescript sounding paper called Deterministic Non-Periodic Flow. So here's the real guy, this is Ed Lorenz. And there is now so he's a professor of meteorology at MIT. There is now a Lorenz Center for Climate Change at MIT. And he wrote in the abstract of this paper, he said, it is found that solutions of these particular equations are ordinarily unstable with respect to small modifications, so that, this is the important part, so that slightly differing initial states can evolve into considerably different states. And then they say, the feasibility of very long-range weather prediction is examined in light of these results. And so what I'm going to show you is the results from actually Lorenz's original model. And the model is ridiculously simple. But he had the insight that he saw this funny thing happen on his computer, and immediately he had the brilliant insight that it had deep implications for were we ever going to be able to make weather predictions that are longer than a couple weeks. Because you might ask, like, oh, maybe, so why can't we predict weather 4 weeks from now? Is it just like our computers aren't good enough, or maybe in 10 years we'll be able to do it? The answer is no. It's very unlikely that we will ever be able to make accurate predictions of weather more than a few weeks in advance. And he sort of saw this based on a very, very simple model. So the model we're going to look at is a very simple model of fluid convection that's called Rayleigh-Bernard convection. So this is named after Lord Rayleigh's old school guy. Bernard's another fella. So the idea is we're going to consider the flow of a fluid that's sort of trapped in like a box between an upper plate and a lower plate that are made of metal. And the lower plate is going to be held at a warmer temperature, and the upper plate is going to be cooled. And so, because the warm air, we can think of it as water, the warm water is going to want to rise. So you're going to, so at the bottom, you're going to sort of warm that water. It's going to expand a little bit, get a little bit less dense, and it's going to want to rise up. And what you typically find in this situation, so gravity's acting downward, is that it develops these circulations that are called convection rolls. So they're just called rolls because they're circular patterns, and so you have warm fluid rising, and then cold fluid at the top sinking down. And here's a simulation, very simple simulation of the Lorentz model. So we start off with the lower plate is warm, the upper plate is cold, so we have warm temperatures on the bottom, cold temperatures on top. And then after a little bit of time, this circulation develops. So the arrows are showing the velocity vectors. And what's happening is that some of this cold fluid from the top gets brought down, some warm fluid from the bottom gets brought up, and then these two blobs kind of mix because of thermal conduction, and it reaches a sort of steady state like this. And so what Lorentz did was he boiled down the equations of fluid dynamics, so the equations that describe the convection, to basically three main parameters or features. So he said, I'm going to describe this flow, which has temperature, it has velocity, and so forth. I'm going to describe it by three numbers. One is, how strong is this roll circulation? So like, how long are these arrows? How vigorous is the circulation? And he called that X. So he's going to define a mathematical labeling system for defining what's the state of this convection. So X is the strength of this roll circulation. Y is the amplitude of the temperature blobs. So here we have a cold blob here and a warm blob here, so red and blue. So just how dark are those colors? So how cold is the cold blob? How warm is the warm blob? That's called Y. And then Z is the strength of the background temperature gradient. So just overall, how red is it down here and how blue is it up here? So the overall temperature gradient. So there's three parameters: strength of the roll circulation, strength of the red and blue blobs, and then strength of the overall gradient. And he turned that into a mathematical model. And the model, this is just the same movie again. The model looks like this. So he used the fluid mechanics equations to build a model for these three parameters, X, Y, and Z. And the structure of the model in very general terms looks like this. So here, N is the time step. So the way that the model works is you take the data, you take the system state at a current time, and you predict, let's say, 1 second from now what it will be. And then based on that prediction, you say what's 1 second more down the road. It's called a time stepping algorithm. So you advance the state of the system with your computer code 1 step at a time. And the way that it works is that the n+1th step, so let's say 1 second in the future for X, Y, and Z, those are all based on functions of the state at the current time. So if you know X now, which is at time step n, Y now at time step n, and Z now at time step n, if you know those three values, x, n, y, and zn, you can compute all these three right-hand side functions, and that'll tell you what's x at the next step, y at the next step, and z at the next step. And that's exactly how this simulation runs. So I built this simulation in Python. It's very simple, and it just uses math like this to advance the system. And you could, if you took a more advanced course, I would tell you exactly what these three functions are and analyze them and stuff. But for this purpose, it doesn't matter. So these are called the Lorentz equations. He didn't name them that, somebody else named it after. And he studied this system. And he's found something very, very interesting. So now what I'm going to show is, these are two different simulations run with those Lorentz equations, so this model of convection. And these are the initial conditions of the two different simulations. And it's almost impossible to tell, but these two initial conditions are not exactly the same. They're different by about 0.1%. So I went into the initial conditions, and I changed one of the numbers by a factor of 1 in 1,000. So they're very, very slightly different, almost exactly the same. And now let's watch what happens. And so you'll see now, so the temperature blobs are oscillating. This is in a little bit of a different parameter regime than the previous example I showed, so it's more energetic. And so they're sort of following each other. They sort of look similar, but they're starting to look a little bit different. So they're not identical anymore. And now, look, so this one is, they're actually kind of getting decorrelated. This one looks totally different than that now. This one's still moving. It's not fixed. It's going to change later. And so they're doing similar types of things. Broadly speaking, the types of changes that are happening look similar. But even though they were nearly identical at the start, by the time the end of the simulation comes around, this is the final state, you see that they're totally different. So again, it might look qualitatively similar, but look, so here the blue blob's in the middle. Here the blue blob is kind of split between the two sides. We have a red blob in the middle. So if this was weather prediction, so if you were trying to analyze or predict what's the temperature going to be like in St. John's, let's say this particular point in the fluid represents St. John's. Well, simulation 1 tells you it's going to be neutral, about 0 degrees, and simulation 2 tells you it's going to be like 25 degrees. And these two simulations were started with only 0.1% difference in the input data, which kind of tells you, let's say I'm going around making weather balloon measurements, and I'm going to now try to predict the temperature in 2 weeks. If there's only a 0.1% error in my weather balloon measurement, well, that is hopeless, because the two predictions, I can't tell which initial condition I should use, because the error is sort of masks that. And then the final prediction is totally different. So they sort of stayed the same for a while, but then after time, they diverged. And so this was the fundamental thing that Lorenz noticed. And I'll mention that actually when he first saw this, the first thing that he thought was his computer was broken. So he thought there was actually a computer error or some problem with the hardware that caused this, and then did it hundreds of times and checked it and checked it and checked it, and then realized actually he discovered a new field of science. So this is another way of visualizing that behavior. So now what I'm plotting is, so instead of plotting a movie, I'm just plotting the value of x, since that's the circulation strength, the strength of that roll circulation. I'm plotting it over time. And there's a red and a blue curve on here, and that's the two simulations. And so early on, so you can't even tell the difference between these 2 points. They're actually not identical, but they're almost exactly the same. And then up until about time equals 10, they execute these interesting oscillations. And then around at t equals 10, they start to diverge from each other. And then after that, they basically become completely uncorrelated. So the behavior of one is just sort of different than the other. You can't predict one based on the other after a certain time horizon. So by t equals 15, the two solutions are totally different. And you would never want to use the blue to predict the red. It's a terrible prediction, although early on it would be okay. So this is called sensitive dependence on initial conditions, also called SDIC is the acronym. And it just means that a tiny, tiny error here is okay for a while, but then there's this explosive difference, and they completely separate. And this is an absolutely generic thing that happens in weather models, climate models, anything to do with fluid mechanics always works like this. So the implications for weather prediction, I already sort of mentioned, are quite important. Because the first thing we do is we observe the atmospheric state with weather balloons, and these will have small errors. And so those errors are like that 0.1% difference. And so when we run our weather model, which is very similar to the Lorenz model, just a lot more complex, due to those tiny errors will propagate into major differences between two simulations. And we don't know what the correct initial condition is, because we can only measure it with a certain accuracy. So we can't tell the difference which is the correct simulation, simulation 1 or simulation 2. We just don't know. And there could be many, many other ones that you could make, 10, 100 simulations. They'll all give these sort of random answers, and you just can't tell. And that's the fundamental reason why weather prediction is hard. But what about climate? So climate, it turns out, is a lot more predictable. So this is a famous diagram called the Lorenz butterfly, or the strange tractor. Also, I actually just want to mention one thing that I forgot. So if we go back to this picture, it shows that even tiny differences in the initial conditions lead to these major differences later. And you may have heard of this. Everyone has come across this, the idea of the butterfly effect, right? And so the idea of the butterfly effect is that if you have somewhere on the Earth, there's a butterfly and either flies and flaps its wings or doesn't, and that could have an effect on a hurricane trajectory. That sounds ridiculous. I've thought about that a lot in my life, and as far as I can tell, that is literally true. And there's no way around it, and it's just in the math. So the difference between the red and the blue curves here is the difference of a butterfly's wings, and eventually you see differences in these two trajectories. So the butterfly effect is literally true, and in the simplest possible terms, the butterfly does affect the hurricane. Now, and this is a different sense of the word butterfly. So this famous picture is called the Lorentz butterfly. And how you make this is, remember, so the system, the convection system, has these three variables: the strength of the roll, the strength of the blobs, and the strength of the temperature gradient. And that's x, y, z. And so when you have 3 points, you can plot it as a point in three-dimensional space. And that's what this plot is. So I just took that simulation, and now I'm graphing the state of the simulation rather than as a movie, as a point in three-dimensional space. You have the x-axis, y-axis, and z-axis. And what you see is that it has this very interesting shape. It's like a two-winged, these two wings are sort of at an angle, and it sort of circles around, and then sometimes it jumps between these two wings. And this, the fact that it has this structure is actually kind of very, very clarifying. And this really represents the climate of the Lorentz model, because it says we can't necessarily tell how it's going to jump between or how it's going to spiral around, but we can tell in general terms what this model will tend to do is stay on these two wings. It's very unlikely to be up here. It's very unlikely to be down here. Where it will always be is on these two what are called attractors. These are these places in this space where the model likes to live, and it's this complicated structure. Actually, if you've heard of fractals before, this discovery also was central to the idea of fractals, because it turns out this sort of looks like it's almost like a plane, like a two-dimensional sheet here and a two-dimensional sheet here. It turns out this is actually not exactly two-dimensional. In math, it's actually between 2 and 3 dimensions. So that is a strange concept. What does it mean for something to be between 2 and 3 dimensions? It turns out in math there is a way to make that precise, and this has a dimension of something like 2.1 or something. So it's called the fractal dimension. So even though we can't predict, based on because of these initial errors, we can't predict exactly where the system's going to be, in 2 weeks. We can say, well, it will probably be on this attractor, because that's where it always hangs out. So this is kind of like saying, well, in September we tend to have a certain kind of weather. Like in September we tend to be here, and then maybe at a different time of year this butterfly would look different. And so even though the weather prediction problem is very, very difficult and it's actually impossible over long time scales, the climate is still more predictable and more regular. Okay, so the next part is about actual weather systems, but I think I'll leave that for next class. So I'm just going to stop there, and please go take a look at Brightspace for the next assignment. I think almost all the material we've covered, just this weather system stuff, we'll cover on Wednesday. I think then you should have everything you need. Please let me know if you have any questions, and other than that, I will see everybody on Wednesday.